From the Institution of Electrical Engineers, founded 1871, incorporated by Royal Charter 1921, Savoy Place, London. The mechanism of subharmonic generation in a feedback system by John C. West, PhD Associate Member, and John L. Douche, PhD Graduate. And the response of remote position control systems with hard spring, nonlinear characteristics to step function and random inputs by West and Nikiforuk. Discussion. This is a reprint from the Proceedings of the Institution, Volume 102, Part B, Number 5, September 1955. The mechanism of subharmonic generation in a feedback system, July 1954. Summary. The paper was first received 25th February in its revised form 30th April 1954. It was published in July 1954 and was read before the measurement section 15th March 1955. Summary. A theory is presented for the mechanism of subharmonic generation in a nonlinear feedback system. This phenomenon is the occurrence of components in the output of a system whose frequency is a fraction of the input frequency. This subharmonic component is regarded as an oscillation of the closed-loop feedback system in the Nyquist sense. The parameters of the system are modified to allow continuous oscillation by the action of the input signal on the nonlinear element. A connection is shown to exist between the open-loop frequency response and the conditions necessary for subharmonic oscillation. From this, sufficient limitations are obtained to ensure the absence of the phenomenon. Experimental work on a system with a cubic characteristic is included. Many types of nonlinear feedback systems exist, which, when subjected to certain sinusoidal inputs, produce an output whose lowest frequency component is a fraction of the input frequency. A common example is the relaxation oscillator, which can be set in continuous oscillation at a frequency much lower than, but synchronized with, an input or control signal.
Enjoy Stingray music free on your
An
mobile.
LCR resonant circuit with an iron cord inductor as a nonlinear element can be set in oscillation at a frequency near that of natural resonance by the application of a suitable alternating voltage of twice this frequency. A moving coil loudspeaker with non-uniform magnetic field is another example of a device by which submultiple harmonics can be generated. This phenomenon can also occur in a class of remote position control servo mechanisms where saturation of the amplifier or motor provides a suitable nonlinear characteristic. In all these cases, the low frequency present at the output in a submultiple of the input frequency and is usually at or near the natural frequency of oscillation. For this reason, the phenomenon is known as subharmonic resonance. Because of the resonant nature of the phenomenon, the subharmonic component is often of large amplitude, so that the output is considerably different from that obtained when the phenomenon does not occur. For systems in which the output is intended to reproduce the input as closely as possible, as in the motion of a loudspeaker cone or of a servo motor, or for systems intended to respond only to a band of frequencies, this phenomenon can introduce an intolerable distortion. Hence, it is of importance to lay down conditions on the parameters of the system to ensure the absence of the phenomenon. It does not occur in linear systems, and must therefore depend on the nonlinear characteristic involved in the system. In a practical system, it may be inconvenient or impossible to modify the form of the nonlinear element. In this case, it is important to decide how to modify the linear elements to eliminate subharmonic resonance. Conversely, there may be fields of application for devices where the phenomenon is desirable. It will then be necessary to derive the form of a suitable nonlinear element to ensure subharmonic generation. Previous work has accounted for subharmonic resonance by the solution of a nonlinear differential equation, in which the nonlinear characteristic is expressed as a power series. There are two objections to this method, since the output of the nonlinear element is expressed as a power series of the input. Successive approximations to the correct solution converge rapidly only if the amount of nonlinearity is small. Thus, the method is inapplicable to many practical systems where sharp changes of slope occur, saturation effects. So read about the mechanism of subharmonic generation, the describing function, the experimental nonlinear elements, the response of the system. The frequency response of the system in the absence of subharmonics may be evaluated using known techniques. In conclusion, a method has been presented giving a graphical analysis of the generation of subharmonic frequencies. These subharmonics are shown to be due to the input signal modifying the response of the nonlinear element to a further signal. This can result in a phase change for a further signal whose frequency is a submultiple of the input frequency. In this manner, a system which is expected to be stable for all inputs may produce troublesome forced oscillations. General criteria are developed showing the conditions for the absence of these subharmonic oscillations. Experimental work agrees with these results for a particular system. Further work is proceeding on the analysis of systems where the nonlinear element is directly coupled into the feedback loop. In this case, a second-order subharmonic may be generated owing to a steady voltage at the input to the nonlinearity, making its response asymmetrical in form. In such cases, calculation of the describing function becomes extremely laborious. References include Haishi, Subharmonic Oscillations in Nonlinear Systems, American Journal of Applied Physics, 1953, Pedersen, Subharmonics and Forced Oscillations in a Dissipative System, Danmarks Naturvidenskabslig Samfund, 1933. Stoker, J&J Nonlinear Vibrations, Interscience Publishers, New York, 1950. Koschenberger, A Frequency Response Method for Analyzing and Synthesizing Contractor Servo Mechanisms, Transactions of the American IEE, 1950. Institute of Electrical Engineers. West J.C., The Nyquist Criterion of Stability, Electronic Engineering, 1950. Williams F.C., Electronic Servo Simulators. West J.C., The Frequency Response of Certain Case of Nonlinear Feedback System. West J.C., The Behavior of a Remote Position Controlled Servo Mechanism and Hard Spring Nonlinear Characteristics. Johnson E., Sinusoidal Analysis of Feedback Control Systems Containing Nonlinear Elements. Nyquist H., Regeneration Theory, Bell System, Technical Journal, 1932. So read also about the response of remote position control systems and hard spring nonlinear characteristics to step function and random inputs. This paper is concerned with the response to step function and random inputs of a closed loop system having a specific class of nonlinearity called hard spring. In order that an analysis be carried out for step function inputs, the system is restricted to that with a second order characteristic equation. Two amplitude characteristics are considered, the first being a continuous curve and the second being composed of segments of three straight lines. Experimental system is described and the results are compared with analysis. Stabilization is achieved by velocity feedback, but derivative of error stabilization is also considered. A discussion of the effect of the nonlinear characteristics on the overall stability of the system is included. The response of the system with the straight line characteristics is obtained for random input and the presence of noise. Detailed results and a discussion of their implications and value compared with transient and frequency response testing are given. Theoretical verification is not included. In many nonlinear feedback systems, the nature of the nonlinear characteristic determines some distinctive feature in the system behavior. This is usually of an undesirable nature, but occasionally a particular type of nonlinearity yields one feature which may find a field of application. Such an interesting characteristic is the hard spring. Recent work has shown that the introduction of a hard spring nonlinearity actually describes the response time, apparently without affecting stability. Read about the cubic characteristic, degree of damping, extension of Linehart's construction, the phase plane portrayal of the step response. Pattern of the response is displayed on the phase plane. Second order simulator possessing a segmented line characteristic. The analog computer. Analysis of the straight line segmented system. Experimental results using the segmented characteristic. Derivative or error stabilization. Base analysis. The transient behavior of linear system with an amplifier of gain. Stability considerations. the necessity for experimental testing with random inputs, the noise spectra, spectrum analysis, the effect of nonlinearity on experimental techniques. So read about West and Nicky Forks, the response of remote position control systems with the hard-spring nonlinear characteristics to step function and random inputs. In conclusion, the transient response of a system stabilized by output velocity feedback and incorporating a hard-spring amplitude characteristic has been analyzed graphically for two forms of the characteristic. The salient features of the nonlinear response have been discussed and compared with the response of the equivalent linear system. It has been shown that under certain conditions the response of the former is better than that of the latter. The effect of the phase advance stabilization has been derived, and the response of a system incorporating the stabilization has been compared with that of a system stabilized by velocity feedback. It has been shown that the response time of a system stabilized by phase advance is less than that of a system stabilized by velocity feedback, and furthermore, that the first overshoot of the former is greater than that of the latter. The effect of the nonlinear amplitude characteristic on the overall stability of the system has been discussed, and a comparison has been made of the stability of the system with that of a system incorporating a high-gain amplifier. It has been shown that under certain conditions the former is more stable. Experimental verification is included. The effects of nonlinearity on the experimental techniques necessary for testing nonlinear control systems subjected to random inputs have been discussed and experimental results obtained. It has been shown that the contribution to the output by cross-modulation products is negligible, and consequently the output spectrum can be related to the input spectrum to obtain a gain frequency characteristic. Thus, the response to white noise signals has been determined. It has been shown that the effect of increasing the signal and or nonlinearity is to increase the bandwidth and to decrease the resonance peak of the response. The effect of noise on the response to sinusoidal signals is to quench the jump phenomena if it is present, to reduce the resonant peak and to increase the bandwidth. It has been found that for this nonlinearity there is a particular amplitude of sinusoidal signal at which a maximum amount of noise is required to quench the jump phenomena. This suggests that by pre-amplifying the input by a controlled amount of a similar system properly designed might be used as a low-pass filter when the signal is relatively sinusoidal. Finally, the response of the system to a random signal in the presence of white noise has been found to be of the same character as the response to sinusoidal and white noise inputs. One of the chief aims of this work is to determine whether a qualitative relationship exists between the frequency response, transient response, and random signal testing. A comparison of the results in section 11 with those in section 5 and reference 1 reveals that the increased bandwidth and decreased resonant peak of the sinusoidal response related to an increased bandwidth and decreased resonant peak of the random signal response and to a quicker or less oscillatory transient response. There is therefore a definite qualitative relationship between these three forms of testing, and this qualitative relationship agrees favorably with that which exists for the linear system. References include West, Nikiforuk, The Behavior of a Remote Position Control Servo Mechanism with Hard Spring Nonlinear Characteristics, McDonald D, Multiple Mode Operation of Servo Mechanisms, and West C, Dalton R, the step function response of an RPC servo mechanism possessing torque limitation. Also West C, Douche L, and Naylor R, the effects of the addition of some nonlinear elements on the transient performance of a simple RPC system possessing amplifier saturation. West C, Douce L, the frequency response of a certain class of nonlinear feedback systems. Liner A, Étude des oscillations entretenues. West C, Textbook of Servo Mechanisms. William C, Ritson U, Electronic Servo Simulators. Ritson U, Ahmed H, Design and Testing of an Electronic Simulator for Hydraulic Remote Position Control Servo Mechanism. Andronow, Chaikin C, Theory of Oscillations. Mikkel L, Porter A, The Effect of Friction on the Behavior of Servo Mechanisms at Creep Speeds. Wiki R, The Relation between Force and Velocity in Human Muscle. Koscheberger, a frequency response method for analyzing and synthesizing contactor servo mechanisms. Blumenthal and Beck, transient analysis of nonlinearized single-lag servo mechanisms. Pellegrin, application of the statistical technique to the servo mechanisms field, automatic and manual control, Butterworth's scientific publications. Joan S., the determination of the best form of response for a servo with an extraneous random disturbance is present with the error signal. James M. Nicholas B., Theory of Servo Mechanisms, Boot and Nonlinear Control Systems with Statistical Inputs, Dynamic Analysis and Control Laboratory. Sard O., Calculate Frequency Spectrum of the Shot Noise from the Multiplier Tube, Journal of Applied Physics. Hammond Smith, an experimental study of the response of on-off controlled servo mechanisms to periodic and randomly varying input signals. So read all about the mechanism of subharmonic generation in a feedback system and the response of a remote position control systems with hard spring nonlinear characteristics to step function and random inputs. I repeat, the mechanism of subharmonic generation in a feedback system, the response of remote position control systems with hard spring nonlinear characteristics to step function and random inputs.